weathering climate change. And I'm actually putting some material into this talk that's not in the book. And I'm already thinking of doing a second edition for that book. So I'll be sneaking in some new material here. And I do take questions on Facebook and Twitter, as do the rest of the staff scholars at Reasons to Believe. And if you're not already a subscriber, we have a 24/7 YouTube channel, and you can subscribe for free. And every day we're putting new video clips up there. So, and we're giving away a free chapter of Improbable Planet at reasons.org/Ross. I have one chapter there on climate change, and that got expanded into an entire book, Weathering Climate Change. And you can get a free chapter at reasons.org/Ross. And if you really want to see climate change, go to Canada. This is a photo of my wife in the first week of July, where the temperature went from 80 degrees down to 20 degrees in the space of just a few hours. And Canada is experiencing climate change at a rate that's 5 times greater than the average for the rest of the world. And it's impacting their winter climate as well as their summer climate. But yeah, you can get a free chapter of the book. Anyone can get a free chapter of the book at reasons.org/Ross. Okay, weathering climate change. And I'm going to begin by making the point that in order to have billions of humans living at one time on our planet, we have to be living at a time in Earth's history where there is an ice age cycle. And an ice age cycle is where the coverage of ice on the planet oscillates between about 10% and 20 to 23%. So this is the ice coverage of North America right now. You can see Greenland and some of the Canadian Arctic islands. Then you see that there's ice over parts of the western mountains of the United States and the Coast Range of British Columbia, Alaska. And this is what it looked like during the height of the last ice age, where 55% of North America gets covered by thousands of feet of ice. And actually the ice penetrated, thousands of feet of ice penetrated all the way into Southern California. And in the wintertime, the port of San Diego was clogged with ice, and even some of the ports on the Pacific coast of Mexico. And this is what it looks like right now. So right now we're in what's called an interglacial. And the ice age cycle currently has a periodicity of about 100,000 years. And so and then the glacials last a lot longer than the interglacials. And so you get about 90,000 years where the ice coverage is about 20 to 23%, and you get anywhere from a 5 to a 10,000 year period where it's just 10,000 feet of ice. And the benefits we get from living in an ice age cycle, the reason why you have to be living in an ice age cycle in order to be able to sustain billions of human beings, is that it takes the melting of glaciers left over from the last ice age, glaciers and ice fields left over from the last ice age, to water the great soil-rich plains of the earth where we grow the food that we need for ourselves and our domesticated animals. And well, this slide basically shows you that you got these, everywhere where you see that blue on the continental land masses, that's where you have a minimum 1,000 feet thickness of ice during the last ice age. And it's the melting of that ice that's been feeding the great rivers of the world that flow into the agricultural plains that we have. And it's flowing to this very day. And so it's these melting glaciers that provide the water that we need to grow all the food. But the other thing that's been recently discovered is that, with the ice age, and what we've been noticing is that because of the rise of the Tibetan Plateau, each successive ice age becomes greater than the previous one. So it started off being about 18% ice coverage. The last ice age was 23% of our planet was covered with thick ice. And that ice melts very quickly. So for example, you got 3,000 feet of ice over Canada, and that melted away in less than 1,000 years. And it's the rapid melting of that ice that causes a strong wind to blow off of the mountains and high plateaus that have been recently denuded of ice, and causes this rich, iron-rich and nutrient-rich dust to flow off of these high plateaus, and it gets dumped onto the plains. And that's particularly true of the North American prairies and the Chinese and Indian agricultural plains. They benefit enormously from this wind-blown dust that came off just as the ice was rapidly receding. The other thing that happens is when thousands of feet thickness of ice melt, you get a rebound, because what happens, all that ice pushes down on the continental land masses, pushing them in towards the mantle of the earth. And when that ice melts, you get a rebound. The continents rebound back up. And when they do, that ignites volcanic eruptions all over the world. And so roughly about 13 to 15,000 years ago, there was these huge volcanic eruptions that took place as a result of that rapidly melting ice. And that, again, caused very nutrient-rich dust and ash to fall on the great agricultural plains. So it's a combination of that water and these two fertilization events that actually makes it possible for us to feed billions of human beings during the warm interglacial period. And if you pick up weather and climate change, I list about a dozen other benefits we get from living in an ice age cycle. And so that's what makes it possible to have our civilization. But here's another benefit. This is Yosemite Valley. And during the last ice age, there were thousands of feet of ice that was all over this part of south central California. And the rapid melting of that ice caused this canyon to be carved out. And so there was no El Capitan, there was no Half Dome, there was no Yosemite Falls. All that was created by the rapid retreat of ice during the last ice age. And this is true all over the world. The fjords of Norway were all carved by retreating ice from the last ice age. Likewise, the fjords you see in British Columbia and Alaska, they're all carved out. Even the harbor that you see in Tasmania and Hobart, that was carved out by the retreat of ice in the last ice age. So we got these great harbors around the world, but we also have these scenic wonders. So what you see here in this photo, and here's one that I took in a hike I made in British Columbia, where we actually have, this is just a few, I counted 25 giant waterfalls flowing over these cliff walls in this 3-mile long box canyon in central British Columbia. And again, this was carved out by retreating ice from the last ice age. And so we live at a time on planet Earth where we got scenic beauty like we've never had before. And Ken's going to be talking about the beauty principle. And I can just tell you that I found it so much easier to share my Christian faith with atheist scientists when I take them on a hike into the high Sierras of California than I do in the hallways at Caltech. There's something about beauty that really enables you to begin to consider the most important things of life, the spiritual things of life. And that God has put us here on planet Earth at a time when our planet has never had the scenic beauty that it's had before. And I think he knew that we were going to need to have some relief from our high-tech urbanized civilization. Now, stars are kind of like human beings. They're unstable when they're young, they're unstable when they're old, they're maximally stable when they're middle-aged. But stars are different from human beings, and at the time of their stability is very brief compared to the lifespan. I mean, we humans are stable for more than 90% of our lifetime. That's not the case with stars. it's much less than that. And so, for example, this shows you the flaring activity and the X-ray and ultraviolet radiation intensity that comes out of a star like our sun. And that y-axis there is logarithmic. When the sun was young, it had a flaring activity level that was more than 100,000 times what it is right now. And in the future, the flaring activity is going to return. That little dotted line there shows you where we are right now. The sun's about 4.57 billion years old, and that's the time when its flaring activity is minimal. This is true of all stars, but it's stars that are the mass of the sun that have the minimum flaring activity and the minimum X-ray and ultraviolet radiation pouring out from it. So we happen to be orbiting the most stable star at the most stable time in its history. But this poses an enigma, and the enigma is this, okay? The flaring minimum occurs when the sun is about, and this is true of all stars, when they're about halfway through their nuclear burning cycle is when they're most stable. But in terms of having extreme, this is something that's just been recently discovered. Our star, the sun, is at least 5 times more stable in its luminosity than any other known star. And there's evidence showing that this extreme luminosity stability is relatively short-lived. And guess what? We're in the middle of that very stable period. But the enigma is this, that our sun, as it converts hydrogen into helium in its nuclear furnace, causes that nuclear furnace to burn ever more efficiently. The efficiency depends on the density of the core, and when you convert hydrogen to helium, that makes the density ever greater. And so it explains why the sun's been getting brighter and brighter throughout the history of life here on planet Earth. So today, the sun is brighter than it's ever been in the 3.8 billion year history of Earth. And for 90% of that history, our planet has had no ice. Ice is relatively rare in the history of our planet, and yet today we've got ice. We got ice that's at least 10% and goes up to 23%. So that's a lot of what I talk about in weathering climate change. We know we need to be living in an ice age cycle, but how do you get ice on a planet that's been ice-free for 90% of the history of life? And, we shouldn't be having any ice at all. And if we do have ice, what explains all this ice in the face of the sun being brighter than it's ever been before? Well, there are tectonic events that are responsible that I talk about in An Improbable Planet and Review and Weathering Climate Change. But what's new that's not an improbable planet is that the most important factors are 3 asteroid collision events. And the first of those events occurred 2.58 million years ago off the south tip of South America. And this event was actually discovered serendipitously. There was a ship that was exploring the bottom of the Pacific Ocean, and they noticed an anomaly off the south tip of South America. They were seeing chemicals there that you only get from a giant asteroid collision. And for about a 20-year period, they surveyed the area and discovered that to explain the amount of debris at the bottom of the ocean, and we're talking 17,000 foot depth. So it's a deep part of the Pacific Ocean. And they found the signature of an asteroid collision that extended over an area that measured 500 kilometers by 300 kilometers, and determined that this had to be an asteroid a minimum of 1 mile in diameter, and may have been as large as 2.5 miles in diameter, that hit the Pacific Ocean at this time. And they were able to date it as 2.58 million years ago. And interestingly, that was consistent with the dates of tsunami mud deposits they found all around the Pacific Rim. And recently, they even found it in the Atlantic and even in the Mediterranean. So for example, you can you can go visit the Adriatic Sea on the east side of Italy, and you'll find evidence of an ancient tidal wave that was 1,000 feet high that piled up mud on the shore of Slovenia and Italy. And this is true all over the Pacific. And so they're able to determine that to explain a tsunami, I mean, we're talking 1,000-foot waves running through the Atlantic and the Pacific, and that what they saw at the bottom of the sea basically told them that there must have been a giant cloud of aerosols over the entire planet that lasted for several years. And it'd be equivalent to what Carl Sagan referred to as a nuclear winter. You know, if all the nuclear bombs in the world were exploded at one time, it would actually cause an aerosol cloud to block out the light of the sun. Same thing happened 2.58 billion years ago. And what that did is it initiated the ice age cycle. Now, before that event, there was ice on Antarctica, but this caused a much bigger buildup of ice on Antarctica and initiated the buildup of ice on Greenland, the Tibetan Plateau, and elsewhere. So if it wasn't for this asteroid hitting there in the South Pacific, we would not have had an ice age cycle. So that ignited the ice age cycle. And then there was a second asteroid that hit, and it might have been a comet because we've actually found multiple, here we go. They found multiple craters, at least two, and now they're looking for a third one. And so that blue circle you see in the South China Sea is where they found the biggest crater. If you look off to the left in Laos, you'll see a second crater. A little blue ellipsoid there, and Laos indicates that probably this was a giant comet that broke up as it was going through the Earth's atmosphere and hitting these two locations. And a paper's been published making the point that before this event, what is now the Spratly Islands was actually a fairly big, significant island. But this comet hit with such force, it obliterated this island and left these tiny specks that we call the Spratly Islands today. And that red circle you see there would be the minimum crater size. The blue circle would be the maximum crater size. And that blue ellipsoid you see in Laos, that would be the minimum crater size. But what this did is it was one of multiple factors that contributed to changing the cycle of our ice age cycle from about a 41,000 year period, which is what happens because of the variation of the tilt of Earth's rotation axis, to a 100,000 year cycle. Now, when it was 41,000 years, that meant your warm interglacials were lasting only 1,000 to 3,000 years. But now that the cycle has been changed to 100,000 years, and this comet basically sent up a cloud in our solar system that the Earth passes through every 100,000 years. And again, that's just one of multiple factors that happen all simultaneously that changed our ice age cycle from 41,000 years to roughly 100,000 years, which means the warm interglacials now can last long enough that it's possible to launch civilization. With one gigantic caveat, what we're noticing in the ice age cycle, this is a temperature record from Antarctica, basically showing that whether you're in an interglacial or a glacial period, whether you have significant temperature variations taking place all over the Earth. And this is going to be a problem for launching and sustaining civilization. Now, it's actually much more dramatic than what you see in this slide. And so here's a detailed record from the last glacial, when there was thousands of feet of ice covering our planet. And it shows a combination of the temperature records here from both Antarctica and Greenland. And what you notice here is that the global mean temperature is jumping up and down by about 10 degrees centigrade, 18 degrees Fahrenheit, with periodicities of just a few centuries. And this means that it's really not going to be possible to launch and sustain global civilization. We now, let me pull someone. Okay, someone's in the waiting room. I hope one of you is a co-host who can admit Jesse. Thank you. Thank you for taking care of that. Okay. We now have evidence that humans living during the last ice age were just as technologically capable as we are, but because of this extreme climate instability, they were not able to launch and sustain any significant civilization. We now have evidence that they had the technology to make baking hearths, to grind grains, to roast them, and to make bakery products out of them. This goes back at least 34,000 years. We now have evidence that humans living during this period were collecting these stainless steel asteroid meteorites and converting them into sophisticated, so metallurgy does not go back just 3,000 years like you see in your textbooks. We now know that it goes back previous to 10,000 years. People were actually making these stainless steel tools long ago, and written language goes back a long time. We now have evidence on the west coast of North America that the American natives there were making these totem poles that were recording events that were taking place during the last ice age. But it was all on a small scale. Agriculture was happening, but it was on a very small scale where farmers were growing multiple crops because they had no idea which crop was going to fail and which crop was going to succeed. It was simply not possible to scale things up. But what happened was there was another asteroid that hit that for the first time, so for 2.5 million years, this is what was happening during the ice age cycle, that you had these extreme climate instabilities taking place. And the only time we have in the entire ice age cycle where you got a stable climate has been the last 9,500 years. So in the entire ice age cycle, there's been no climate stability except for the previous 9,500 years. And whoops, let me pull that back for you. This is what's called the Younger Dryas cooling event, where typically the temperature rises from an ice age into an interglacial, where the temperature rapidly rises to about 2 degrees centigrade above where we are right now, and then rapidly drops back down into an ice age. Typically, the interglacials are very short-lived. The temperature jumps up to this maximum and then drops right back down into an ice age. The exception is the ice age cycle we're in right now. So as the temperature was rising, as with the result of the melting of the ice caps, something happened that dropped the temperature back down and dropped it down by over 8 degrees centigrade. And so that dotted line represents what we call the Younger Dryas cooling event. Bottom line, it prevented the temperature from jumping up to its typical maximum of 2 to 3 degrees centigrade above where we are right now. And just before I brought the book out, they discovered a crater where a giant asteroid had hit. And actually this crater, it was discovered accidentally. A NASA aircraft was flying over northern Greenland. They happened to have their ice penetrating radar on, and they discovered that there was this giant crater under 3,000 feet of ice in northwestern Greenland. This actually shows you the size of the crater, and they sent a team of geophysicists to the site, and they're able to measure the meltwater coming out from the Hiawatha ice field here, and the meltwater had the isotope signatures of a giant stainless steel asteroid. And the impact of this asteroid hitting, number one, it brought about a cooling event as it caused rocks and ice to go up into the atmosphere. The dust and the rocks blocked out sunlight, and then you got all this ice falling all over the North Atlantic. But probably the biggest climate impact it had is what it did to Lake Agassiz. And so as thousands of feet of ice were melting from Canada and northern United States, it produced this gigantic glacial lake known as Lake Agassiz. And so here is this huge lake filled with glacial meltwater, and the glacial meltwater was draining down through the Mississippi into the Gulf of Mexico. But with this asteroid hitting in northwest Greenland, it caused giant rocks to pelt throughout the northern part of North America. And what it did is it blocked the flow of water. And so the flow through the Mississippi became blocked because of this bombardment. And the bombardment opened up two new pathways for the meltwater to get into the oceans. And one was through Great Slave Lake and Great Bear Lake, and the Mackenzie River into the Beaufort Sea of northern Canada, and the other was through the Great Lakes and out through the St. Lawrence. And the meltwater flowing into the Beaufort Sea met an ocean current as a result of the melting ice in the Arctic Ocean, and it causes cold glacial meltwater to flow eastward through the Canadian archipelago and down between Baffin Island and Greenland out into the North Atlantic, where it melted cold glacial meltwater coming out through the St. Lawrence, also into the North Atlantic. And what this did is it turned back the Gulf Stream. As you're probably all aware, what keeps Europe warm is this warm water from the tropics of the Atlantic moving up through the Atlantic and warming Europe. But this glacial meltwater basically turned that back. And so it cooled down Europe, cooled down Siberia. North America was cooled down, actually cooled down the entire world. We now know it had a cooling effect that was global and basically prevented the temperature from jumping up to its normal maximum. And if it were to jump up to its normal maximum, it would melt the polar ice cap. And when you melt the polar ice cap, instead of the Arctic area reflecting sunlight with 60% efficiency, if you melt the ice, then the reflection is only 6%, which means that the Arctic Ocean waters are now absorbing a lot more heat. And when they absorb all that heat, a whole lot more water vapor is produced over the Arctic, and that falls as snow over Siberia and Canada. And so that's the enigma of the ice age cycle, is that global warming brings on global cooling. The only reason why Canada and Siberia today are not covered with thousands of feet of ice, they don't get enough snow. The snow deposition is less than 10 inches of a rainfall equivalent. And so snow does fall, but the snow that falls melts during the summertime. But if you were to double the snowfall, then the snow accumulates, transforms into ice, and in a few centuries, you've got Europe, Siberia, and Canada covered with thousands of feet of ice. And this has been prevented from this asteroid hitting, which stopped the ice over the Arctic from melting and causing more snow to fall over Siberia and Canada. But it also shortly after, I mean, literally within 1,500 years after this collision event, it briefly stabilized the climate. And with a brief stabilization of the climate, humans began to expand their technology and their civilization, known as what's called the Neolithic Revolution. And so suddenly, instead of humans doing everything on a small scale, they were able to expand it. And by expanding it, they were able to grow their population. And this has been resulting in a technological revolution that's literally persisted for the last 11,000 years. Now, what was happening is that post this collision event, we now have the changing tilt of Earth's rotation axis, the changing shape of Earth's orbit about the sun, working to cool the planet. So for the past 11,000 years, we've had both the changing tilt of our rotation axis and the changing shape of Earth's orbit working together to cool the planet. But the launch of human civilization counterbalanced that. Humans, through their agricultural activity, their technology, their increasing population, the domestication of animals, all this had an impact. Also deforestation, creating pasture lands. All this had a warming effect. And for the past 9,500 years, the natural cooling that's been taking place in the earth has been counterbalanced by human activity that's been warming the planet. And what you see in that blue line there is a recent temperature determination based on 74 independent temperature proxies from all over the world. And for the first time, we have a really reliable temperature record of the past 10,000 years. And most textbooks tell you that over the past 10,000 years, the global mean temperature has been stable to within plus or minus 2 to 2.5 degrees centigrade. We now know it's been stable to within plus or minus 0.65 degrees centigrade. And this has never happened before in the ice age cycle where we've had this kind of stability. And what you notice here is that that temperature has gradually been dropping over the past 9,500 years. The cooling effects, the natural cooling effects, were actually a little bit greater, slightly greater than the warming effects from human activity. And so over the past 8,700 years, the global mean temperature has dropped by 1 degree centigrade. But if you go to the very end of that curve, you see in the last 70 years has gone up by 1 degree centigrade. So today, the global mean temperature is what it was 8,700 years ago. And that's not a problem. I mean, a 1 degree change isn't going to make any difference. We've had conditions suitable for, advancing our technology throughout that entire 9,500 year period. The concern is that it's taken 8,700 years to decline by 1 degree centigrade. It's gone up by 1 degree centigrade in just 70 years. What's happened since the end of World War II is that the advance of technology has been increasing exponentially. And so at a far more rapid pace than what happened previous to the end of World War II. And if that were to continue and we were to have another degree, another 70 years, another degree after that, we'll wind up melting the polar ice cap. And when we do, we're going to bring on the next ice age. So that's really the concern of people studying climatology, is that we're at risk of raising the temperature to such a point where we're going to reintroduce extreme climate instability like we've had for the past 2.5 million years. But the remarkable thing is that this period, 9,500 years of extreme climate stability, has been matched by several other features that are crucial for our advanced global civilization. And I only have time to consider one. There's a whole bunch in the book, Weathering Climate Change, but one has to do with supernova eruptions. You say, well, what is a supernova? It's where a giant star will explode, and when it does, it'll explode with the energy equivalent of about 100 billion other stars. This shows a supernova in the galaxy NGC 4526. It exploded in 1994, and over a period of just a few months, it goes to a very high brightness and then disappears and becomes difficult to see. And an astronomer by the name of Firestone actually demonstrated that what we've been experiencing for the past 10,000 years is a supernova anomaly. And so he actually looks over the past 300,000 years, and this basically shows you the nearby supernova during the last ice age. And so during the past 50,000 years, we've had 4 such events. And he shows that these events are not so close to us to wipe out human beings, but it's close enough to affect crop productivity. Now, when you're in an ice age, crop productivity drops just because the carbon dioxide level is lower. But another contributing factor to why it was so difficult to obtain food during the last ice age is this is a time when we had nearby supernova, not enough to kill us, but enough to increase the cancer rate. So it would have had an impact on lifespans and human health. And probably its biggest effect would be on crop productivity. Contrasted with a supernova we see over the past, 10,000 years. These are the closest ones over the past 10,000 years. And basically shows you that none of them are closer than 5,000 light years, which means they have no measurable effect on human health or crop productivity. But the whole point is this period where we've had no nearby supernova perfectly overlaps a period of extreme climate stability and overlaps another 10 known windows that similarly make it possible for human beings to have a population in the billions where we get to enjoy the technology that makes it possible to spread the good news of salvation through Jesus Christ to all the people groups of the world in just thousands of years rather than millions of years. And you actually see this in Revelation chapter 7, verse 9, where John has this vision and he says, before me was a great multitude that no one could count from every nation, tribe, people, and language. And this, I think, is well cross-referenced by the end of the book of Matthew, where Jesus makes the point that he will come back when the good news of salvation has been taken to all the people groups of the world, where a significant fraction of those peoples become disciples, faithful disciples of Jesus Christ. And basically Revelation 9:7-9 says, yes, that will happen. Every tribe, nation, people, and language. And it's a multitude that no one could count. And the Greeks at that time had a number system that went up into the billions, which means we're talking at least billions of humans that are going to actually come into a redeemed relationship with Christ. Well, let me spend the past few minutes with what I think is unique about weathering climate change is that, people have referred to my book as the anti-Al Gore book. Al Gore came out with a best-selling book, Inconvenient Truth, where he basically says we're facing a climate crisis. If we don't do something immediately, we're going to basically fall back into a period of extreme climate instability with catastrophic consequences, and basically says we need to do whatever we can to prevent that from happening, and basically was recommending that we take steps that would require enormous sacrifice on the peoples of the world. We all stop driving vehicles if we shut down all of our factories. Basically, if we agree to a standard of living that's 2 or 3 times lower than what we have right now, he claims, and many climatologists claims, that's what's going to be necessary to stabilize the climate in the future. But what I read in scripture are 2 things. Number one, humans are fundamentally selfish. We're all sinners, and therefore trying to motivate billions of people all over the world to make a huge economic sacrifice probably won't work. Their selfishness and their sin is going to say, well, I'll let everybody else sacrifice, but I'm not going to sacrifice. And people will cheat. And we've seen plenty of evidence of that throughout human history. And so having the governments of the world try to pass laws to enforce draconian economic sacrifices, in my opinion, is doomed to fail. It's simply not taking into account this biblical principle that we're all sinners. But there's another biblical principle that's taught in Job and Genesis, is that God had commanded us humans. He says, you are the epitome of my creation here on earth. I'm putting you in charge of the planet, manage its resources, for your benefit and the benefit of all their life, which gives us a biblical principle saying we will not be in a spot in our responsibility to manage the planet where we have to choose between our benefit and the benefit of the rest of Earth's life. We will find win-win solutions. We have just to look for them. And so I fill my book with about 40 different ways that we can continue to stabilize the climate and increase the economic well-being of the human peoples, and especially the poorest peoples, while at the same time we benefit the world's ecosystems. So we can stabilize the climate, enhance the quality of the rest of the life on planet Earth, basically make for better ecosystems, and at the same time stabilize the climate of the world. So I'll just take a couple of minutes here. I don't have time to go into this in any detail, but just some ways we can make that happen. And one is to shrink back the deserts of the world. It's because of human sin and abuse that we've made. This is a photo of the Sahara Desert. And the Sahara Desert today is 10 times the size that it was at the time of the Roman Empire. And this actually shows you the extent of the Sahara Desert. It's now bigger than the continent of Australia. And the reason why it got to be so big is people living on the south side of the Sahara Desert were stripping the land of vegetation predominantly for cooking fuel. And there was a time in the 20th century where the Sahara Desert was advancing southward at a rate of 6 miles per year. It has slowed down since then, but it's still expanding. And so one radical proposal I put in Weathering Climate Change, how about if we give the South Saharan peoples all the kerosene they want? They can burn as much of it as they want for free on the condition they work with us to replant the Sahara Desert. And the Israelis have actually shown how this can be done in just a single generation. And I won't go into the details, but it'd actually be possible to shrink the Sahara Desert within a generation or two back to the size it was during the Roman Empire, which means you could now be planting what is the Sahara Desert with grains. In fact, during the Roman Empire, the food that fed Europe was from the grains that were planted in what is now the Sahara Desert, which means there would be an income source for people living in the Sahara Desert region. Those grains and other vegetation would soak up huge quantities of greenhouse gases, which would turn back to some extent the global warming we're experiencing, and it would restore the ecosystems. So suddenly the animals and plants would begin to thrive in what is now the Sahara Desert. And that could be done in the Gobi Desert. Matter of fact, I think there's going to be a stronger motivation to shrink back the Gobi Desert, because as of 2 years ago, the Gobi Desert has penetrated right into the city of Beijing, China. And so I think the Chinese are going to have a strong motivation to reverse the growth of the Gobi Desert. And you're probably aware there's a lot of concern about what's happening in the Amazon. The Amazon jungle is being cut down at a very rapid rate to be converted into pasture lands so that people can raise cattle and make money. And it's such that more than 20% of the Amazon jungle has disappeared in just the last 30 years. And the concern is that if that were to continue, you reach a point where there's simply not enough forest in the Amazon region to sustain the rainfall that's necessary to maintain that forest. In other words, one of the wettest places in the world could quickly be turned into a dry desert just by deforestation. And so, the Western nations have been basically putting pressure on Brazil to stop this, but they're really not addressing the problem. The problem is this: when you cut down the jungle and convert it into pasture land, the soils are not nutrient rich. Within about a decade, suddenly you can no longer support cattle on that because it basically gets turned into a desert. A better way to motivate Brazil to maintain the Amazon jungle, and therefore to make sure that we still have lots of greenhouse gases being pulled in the atmosphere, is to say, hey, here's a better way to make money. Why don't you go throughout the Amazon and selectively remove the big old trees? Those trees no longer are efficiently pulling carbon out of the atmosphere. They're the slowest growing trees in the Amazon jungle. They're the most valuable trees. And so pull them out before they die, because when they die, they release greenhouse gas to the atmosphere. So you want to harvest them and basically turn that wood into homes and furniture where the carbon can be sequestered literally for centuries. And then you replant. And so you remove one of these big old trees, you plant a young tree, and it's been shown in the scientific literature, young trees grow 2 to 4 times faster than the old trees, which means they're pulling 2 to 4 times as much greenhouse gases out of the atmosphere. And so the best way to make money off of the Amazon would be to selectively harvest those big old trees and replant them with younger trees. Over the course of several decades, you'll make way more money doing that than stripping the land of jungle and converting it into temporary pasture land. And by the way, this needs to be done also in the rainforests of North America and other parts of the world. I grew up in coastal British Columbia, and this is a photo I took through a rainforest, but it's a rainforest where they do not permit any logging to take place. And consequently, when you walk through this forest, notice how hard it is to walk through it. There's dead wood everywhere, dead decaying wood. And that dead decaying wood is releasing greenhouse gases to the atmosphere. This makes it difficult for wildlife because it's so hard to move around in this forest. And instead of, we were to actually say, hey, instead of protecting these forests, let's allow lumber companies to go through there and selectively take out the big old trees that are in danger of dying and sell that lumber, then replant those big old trees with younger trees. And this way you're going to have a healthier forest. The wildlife will thrive because now they're going to be actually able to move around the forest. You're not going to have a whole lot of decaying material that's going to be producing conditions for thorny blackberry bushes, which again poses a barrier to wildlife. And you're going to be pulling many more greenhouse gases of the atmosphere because you're going to have younger trees rather than older trees. And so literally everybody wins in this situation. And then let me just finish with an appeal to thorium nuclear power. This is not in the book. I wrote a chapter on this, but I had to cut it out. In fact, a lot got cut from the book just because we needed to keep the book within a reasonable length. But there's a huge push around the world to try to come up with nuclear fusion reaction. And I would agree that if we come up with a power source where we're converting hydrogen into helium like the sun does, it would produce a huge amount of energy. The problem is we don't have gravity to contain the hydrogen. We have to do that through electromagnetism. And so far, it's not been shown to find any economic way where we can make a magnetic bottle stable enough we're actually able to make nuclear fusion work. I remember when I was a teenager, physicists were saying, we're going to have nuclear fusion reactors producing all the energy we need by the end of the century. Well, we're 20 years past the end of the century, and we're still nowhere near close. But back in the 1960s, it was shown that we can actually get energy from thorium nuclear reactors, just like we do from uranium. But you get way more energy out. 1 ton of thorium produces the energy equivalent of 200 tons of uranium, or 3,500,000 tons of coal. And thorium is much more abundant in the crust of the earth than uranium, so it's much cheaper to mine. And the United States has enough thorium to produce 100% of its total power needs for at least the next 1,000 years. And there's 1,000 times less radioactive waste, and the waste is safe to handle after 200 years. With uranium, it's not safe to handle until 50,000 years go by. With thorium, it's safe within just 200 years, and you can mine it without protective equipment. And unlike uranium reactors, thorium reactors are meltdown proof. It's impossible to get a meltdown, and it can't be diverted to make nuclear weapons, which means we can give these thorium nuclear reactors to all the nations of the world without any worry that they're going to turn them into nuclear weapons. One important caveat: you actually can get nuclear weapons from thorium nuclear reactors, but the people who do it will be killed in the process. So there's no way to get those weapons without being killed, and there's no way to deliver them fast enough. So no one's in their right mind is going to try to make nuclear weapons from thorium nuclear reactors. A decade of construction and scale up could literally provide all the energy needs of the world, which means we wouldn't have to be burning fossil fuels for energy. Say, how cheap would this be? It would actually be cheaper than hydroelectric power. This would literally be the cheapest source of energy that's in use today by at least a factor of 2. And just to give you some context, I have friends living in Canada where, because they get 100% of their energy, electricity from hydroelectric power, they can drive their Tesla cars, 5-passenger Tesla cars. They can drive them 400 miles a week for 50 cents. So they're only paying 50 cents. How much do you pay at the pump? They're paying only 50 cents to drive 400 miles. So again, if you want to learn more, you can check out these 2 books, Weathering Climate Change, reasons.org,